welcome to lecture 24. So, today we will have a short talk on non determinacy. Well, there is a lot of confusion about this word. There is non determinism, which is as opposed to determinism, and determinism is an ism. So, and determinism is an ism. So, it is a philosophy which talks about the eventual, which talks about destiny, fatality and so on and so forth. Determinacy is a property of a system, of the predictability. So, they are closely related, but they are not the same. There is of course correspondingly there is also indeterminacy, which often means you do not know. It might be deterministic. So, indeterminacy usually just means that you do not know. Non-determinacy means that there are several possible choices and you cannot predict which choice would actually be taken. So, indeterminate. So, for example, division by 0 is indeterminate, right. So, non-determinacy is a property of systems by which there are several possible alternatives, maybe an infinite number, but or a finite number, but there is usually at least more than one possibility. And determinacy, the property of determinacy itself is a degenerate case of non-determinacy, where there is exactly one option, right. Okay, so, we were looking at the case statement, and this non-determinacy or choice is really a generalization of the case statement. So, but let us motivate it by an example, right. So, let us take this example. So, the problem is, let us say given an arbitrary positive integer, what you have to find is you have to find the largest m and n such that 2 raised to m multiplied by 3 raised to n divides, let us say, the number a, right. So, you have to find, I mean it's a small part of, let us say, unique prime factorization, where you are restricting yourself to just the powers of 2 and 3, right. So, so let us just look at this. So, given an arbitrary positive integer, of course, when a is 0, m and n are, well, infinite, indeterminate, whatever, but when a is positive, of course, you will have some definite number m and n, right. So, here is a simple Pascal like program segment which just counts the number of 2's and 3's found so far. So, what you would do is you would well, one possibility is just that while you have found that 2 is still a divisor of a, just keep incrementing 2's by 1 and keep dividing a by 2, right. And once you are through with all the divisors of all the divisions by 2, you start with the divisions by 3 and you find all the number of divisors of 3, the number of times 3 divides this number, right. So, now if you look at this, there is an equivalent program, of course, in which I could have flipped these two. So, I could have flipped these two while loops, and it would have it would not have mattered at all. But there is also another equally viable alternative in which I do not care to first find all the divisors of all the number of times 2 divides the number of times 3 divides the number. After all, the two things are really quite independent. So, I could decide to divide it twice by 2 if it does divide, if 4 is in fact a divisor of the number, and then start looking at a few 3's, and then come back to looking at a few more 2's, and then come back to looking at a few more 3's till the process ends. Till it is impossible for me to find the number, is till the number is no longer divisible, let us say by 2, 3 or 6, right. So, now this is a form of, I mean this is a perfectly valid computation, right. I mean it's a fine day, so today I divide by 2's, it is a cloudy day, so I divide by 3's. I mean and I continue this process. I mean after all, why is that in any sense less important as a computation than going about it in such a rigid and straitjacketed manner, right. So, what Dijkstra once coined is that he coined a non-deterministic choice mechanism which works as follows, right. So, here is a non-determinate solution. So, the point is this, here the way the control goes is as follows. You have this choice between these two alternatives. You can look upon this, okay, as checking whether this Boolean condition is true, this Boolean condition is true. And what makes it non-determinate is that both Boolean conditions could be true at the same time, right. I mean it is not necessarily that only one Boolean condition will be true at one time, both could be true at the same time. And so, what I do is I take all these choices and put them all together. I just separate them by this, well, on a keyboard this will probably be square brackets placed close together, but so what I can do is this actually models this phenomenon of mine. I mean I feel like dividing by a 2, so I divide by a 2, then I feel like dividing by a 3, so without exhausting the 2's I do these things in any order. So, if you actually look at the computation defined by this program, then what it means is that there are several possible orders. I mean there is a multiplicity of orders. In fact, there are m n, if m and n are the number of 2's and 3's that divide the number, then it is a shuffling of all those, it is a shuffling of m plus n, let us say the 2's are colored red and red matchsticks, and the 3's are colored with black matchsticks. Then how you shuffle them, all the different orders, it is an exponential number by the way, okay, it is exponential in the number of m and n, right. In how many different ways can you take m cards of one color and intersperse them with n cards of another color, right. So, the number of choices therefore is the number of different possible computations that you can have is actually phenomenally large, but the whole thing is, the whole program itself is deterministic in the sense that there is a single number m and a single number n which the program computes, right. So, if the program were wrong, then, and in the general case, the fact that you have lots and lots of different options open at every stage means that you could also have lots and lots of different answers coming at the end of the program if it ever does terminate, right. So, but what this actually does is that it generalizes, what it actually shows is that a programmer can at many times not want to be bothered about imposing an artificial sequentiality in his computations. Artificial, I mean this program, the sequentiality that it imposes because of the language, because of the design of the language is entirely artificial, right. It has got nothing to do with the notion of computation itself. There is nothing dictated by the notion of computation which necessarily says that it should be done deterministically only in this order or in the other order, right. So, this is a freedom which a programmer might want for various reasons, which I will come to later, but let us just look at another solution, which is actually a more famous solution for this, and it was coined by David Grease from in his, and it is described in his book The Science of Programming. Okay, this is called the welfare crook problem. I have stated a very prosaic and dull version of the problem, but the original problem is actually that well, there are 3 lists of employees at IBM Thomas J. Watson Research Center, students at Cornell University, and people in New York State who are drawing dole welfare, okay, who are drawing government welfare, and unfortunately the laws they have in the country are such that you can't be a full time student and an employee at the same time, you can't be an employee and draw dole, you can't be a full time student and draw dole, and so on and so forth. But apparently there is one guy, that country and that city really breed such people who is actually in all the 3 lists. There is at least one guy who is in all the 3 lists, and the idea is just to find let us say the first one, the first such person. So, bringing the problem down to earth is all we are saying is that there are 3, let us say 3 sorted sequences of numbers with at least one number in common in all the 3 sequences, and what you want to do is to find the least number that is common to all the 3 sequences. So, let us just and I am not particularly bothered about the bounds on the sequences, so I have put a question mark here, but let us assume for simplicity that we have got some large arrays, right. Okay. So, again if you were to program this in any of the standard programming languages, then you will get a deterministic problem of this, you will get a deterministic solution of this kind. As long as you have not found the common element, which is what is represented by this not, okay, do while ai is less than bj, do I is assigned I plus 1, while bj is less than ck, do j is assigned j plus 1, while ck is less than ai, do k is assigned k plus 1, right. And of course, these 3 while loops could be written in any order, right. And the whole point is that when you terminate from this while loop, what you can claim is that for the current values of I and j, ai is greater than or equal to bj, aj bj is greater than or equal to ck, and ck is greater than or equal to ai, and therefore it follows that ai must be equal to bj must be equal to ck. I mean, you can't have a cyclic greater than or equal to relation unless they are all equal, right. So, any permutation of this would do, and of course, one problem is that I mean there are too many while loops in this program. So, maybe what we should do is we should look at another program, right. So, if you look at another program, so is this clear? So, if you look at another program, then what I could do is I could transform all those while loops into just if then statements, right. And after all, there is this loop, this condition that guards the entry into the loop, and so I cannot enter the loop if I have indeed found an I, j and k such that ai is equal to bj is equal to ck, right. As long as, and of course, what happens is that in this case this allows for a far more number of possibilities than the previous one. The previous one was really straitjacketed. Within one iteration of the main loop, you had to first find an I such that ai is greater than or equal to aj, then you had to find a j such that bj is greater than or equal to ck, and you had to find a k such that ck is greater than or equal to ai, and then repeat the whole process till you have found an I, j and k of that kind. This one allows for more possibilities, right. So, it allows for actually well maybe not, but it allows for changing I, j and k in a sequential fashion. I mean, you first change I if it is necessary, then you change j if it is necessary, you change k if it is necessary and go through the process all over again, but it is still totally deterministic, right. It is totally deterministic and therefore, also it is easier to reason with such a with such deterministic programs. So, a non deterministic program for this problem would just be the following. Right. So, there are three conditions. That outermost complicated condition is not necessary, because if all these three conditions are false, it means that ai is greater than or equal to bj is greater than or equal to ck is greater than or equal to ai, and therefore, they are all equal, right. I mean, when does the loop exit? When all these conditions are false, when it is impossible to execute any of these, when it is impossible to go past these guards, these are called guards. So, these things are called guards. So, if you cannot go past these guards, then the loop terminates. So, if there is at least one guard that is true, then you should be able to go past it. Yeah.
So, what does the square bracket indicate?
Well, it's the square bracket is just a syntax, a piece of syntax to separate out the guards. I mean, if you like, it's okay. Will square bracket is just syntactic notion, but it also means that it's a symmetric operation. We'll come to that when we do the operational semantics of this construct. Yeah.
So that indicates indeterminism.
No, these square brackets indicate that there are so many different choices. So if there are m square brackets, then there are m plus 1 different choices. Okay, I mean it's like supposing you are doing addition of a large. Supposing you are doing you are adding m plus 1 numbers, then you have m plus signs in between, right, in the infix notation. So you can think of this as an infix notation to separate out the various choices, right. In particular, so let's look at the syntax. There are two analogous kind of constructs for non-determinate choices. One is the if construct, and this if construct is just says that there are all these Boolean conditions, there are all these Boolean choices, corresponding to each Boolean choice there is an appropriate command to be executed, right. In the case when control enters this if guarded command, all these booleans, or one of these booleans which is true is executed. I mean, you can go past a guard if that boolean is true, otherwise you cannot go past the guard. How, we do not know at the moment, but if bi is true, then ci can be executed, right. And in order to ensure that, since it's much harder, since it's much harder to visualize all the different possibilities, what it means is that the programmer has to be careful enough to ensure, in the case of this if, that he has done an exhaustive case analysis. You can look upon this construct as a generalization of the Pascal case and the if then else put together. If you were to generalize both the if then else and the case, in order to get a new construct, what would you do? The if then else is an asymmetric construct, right? It specifies a clear line of control, right? If you had to come, the case is a nice symmetric construct in the sense that you of course but the case is restricted to enumerated values. So you choose and of course Pascal and whatever from all the semantics that we have done so far, we know that they are all deterministic. So there is only one possibility in the case which can actually be executed. I mean, an expression from our expression language semantics, it is clear that it can have only one value for a given state, and if it is going to have just one value, then there is only one possibility of the case which is true, right. So if you generalize the case and the if then else, then what it means is that you get something like this which has the symmetry of the case statement, but it is not necessarily restricted to enumerations. It is not necessarily restricted to ordinal values. It's a full blown Boolean condition as you would use in any conditional statement. And the fact that you are using full blown conditionals, they could be any Boolean expressions, means that more than one could be true in a given state. If more than one could be true, then it means that more than one of these CIs could be executed, but the if only states that you can execute only one of them. So which means that if more than one is true, there are several different possibilities. So if you execute that if on a Friday, maybe the CI will be taken. If you execute it on a Sunday, maybe you will get or if lightning strikes the earth, maybe you will take some CJ for some BJ which is true. What I mean is it is really non-deterministic. I mean it is an act of God which God is going to be taken, right. It is really, and when I say an act of God, it means that there are reasons which are unpredictable, because of which one particular execution might be chosen, right. In the case of the do, of course, what happens is that as long as at least one of these guards is true, the loop keeps executing, and it exits the moment all the guards are false, right. So let us just look at the operational semantics of these two things. At the moment I will assume that if stands for this thing with guards B1 to Bm and commands C1 to Cm, and the do similarly has guards B1 to Bm and commands C1 to Cm, right. So the operational rule for the if is as follows, and this is what makes, this is the first instance of a rule which actually makes your transition system. I mean we can add these rules to the while, we can add these constructs to the while language, for example, for which we have defined a deterministic set of rules, right. The moment you add these constructs to the while language and give this set of rules, you get the first instance of a non-deterministic transition system, right. All this side condition says is that, all this rule says is that if there is at least one, if there is some BI which is true, then this statement, this if can transfer control to the command CI, period. So if there are two or more different values I and j for which the BI BJ are all true, it does not say which one is going to be executed. It only says that if both BI and BJ are true, since there are, I mean what I mean is there are m different rules for the construct, okay, and all those m different rules, one for each I, and all those m different rules only tell you m different possibilities. Okay. So, if every guard is true, for example, then all that this rule says is that, all that these M rules tell you is that well, one of them can be executed, that is it, one of the CIs can be executed. It does not say anything more, nor does it say anything less. Okay. And just in order to ensure, now the moment you introduce a non-deterministic set of possibilities, what happens is that reasoning about the program becomes far more difficult. I mean, after all, you do not know what implementation will use what policy to choose which guard, which the command corresponding to which guard is to be executed. You can look upon all these guards as forming not a sequence. Sequences, they are written in sequence only because, well, textually you have to write things in sequence. They actually form a set of possibilities. So, any possibility from the set could be picked up and the corresponding command could be executed, right. So, in which case, so okay, and just in, since it's the reasoning process is much harder in this case, because of the fact that there is an explosion of possibilities, the whole transition system now becomes non-deterministic, and so what you have to ensure is that your if statement, if it is non-exhaustive for some reason, then it should come out to be an error. Okay. So, note that I once in the medieval ages said that we never have any negative rules. This is, well, as I was explaining it, it looked like it was going to be a negative rule, that if none of the guards is true, then the if statement gives an error, but actually this, it can be expressed as a positive rule, right. So, so if this disjunction is false, that means none of these possibilities is true, then this leads to an error. Yeah. This should ensure, this kind of thing should ensure that any programmer has to be careful to make an exhaustive list of all the possibilities. It is not necessary that B1 or B2 or up to that the disjunction of all the guards has to be necessarily a tautology. It is not necessary. But what is necessary is, for the set of possible states, it should be possible to prove that only those states are possible which make at least one of these guards true, and the two things are different, right. I mean, if you look at this as a logical formula, it need not necessarily be a tautology, but I might be able to prove about the program before entering the if statement. I might be able to prove that there are only these many possibilities, that the state has to satisfy one of these properties. And so, what it means is that then this disjunction need not be a tautology, in the sense that it need not always be true, but for that set of states alone it should always be true, right. That means there are only certain assignments of values possible for those set of states. Yeah, right. So, for example, in the case of this 2's and 3's problem, what it means is, in the case of the 2's and 3's problem, supposing I require this condition, the meaning of the do is similar, except that it is a matter of exiting, right. I mean, it is in the case of the loop, it is a matter of an infinite computation. I mean, that is the only difference, right. In the case of this, if I know that the state is always 1 in which a is going to be greater than 0, I mean this, supposing, right, if I know that the state is going to be 1 in which a is always greater than 0, then and I have an if then else of the form of something, then it might be just necessary for me to show then this itself is sufficient condition so that these things, the guards need not form a tautology. I mean, let us take a negation of these guards also if you like, right. They need not form a tautology. I mean, it could just be that for that set of states in which A is guaranteed to be initially is always guaranteed to be greater than 0, for an invariant property in which A will always be greater than 0, if the state satisfies that invariant property, then I am guaranteed that, let us say, the loop will exit without any problem. You know, the loop will exit only when all these conditions are true. So, it is not necessary to have this forming a tautology, it is only necessary to ensure that it satisfies an invariant property of the possible states that will actually be encountered before entering this if condition, so that it does not exit in an error. So it is exhaustive in that sense, but it need not be a tautology, right. So the rule for the loop is very similar to our while loop, and it just tells you that as long as some bi is true, you execute the body and repeat the loop. And of course, in the case of the do, we don't there is no question of an error, you have to exit from the loop. So, if all the guards are false, okay, then by the fact that there is no rule which specifies that, it follows that the loop will be exited. Right. The do is actually equivalent to this while loop, and of course, the conditions in all these cases are that there are no side effects caused by the evaluation of booleans. I mean, it's modulo that. So, if Boolean evaluation produces side effects, then it matters how many times you evaluate the Boolean. In the case of the do, whichever Boolean you choose to evaluate, and moreover, if the Boolean evaluations cause side effects, then that adds its own complexion to the program. I mean, it adds its own non-determinacy to the program, which is often unpredictable, which is often implied rather than explicit, whereas the do construct makes the non-determinism explicit, whatever, and if you do not have side effects, then it does not matter how many times you evaluate these booleans, they are going to yield the same value. Note that you are going to evaluate some boolean inside this if, so which means that you are actually evaluating some boolean at least twice in this equivalence, whereas in an actual operational definition of the do, all you are doing is you are evaluating one boolean. You are evaluating booleans as long as they are false, you keep evaluating booleans maybe till one is true, and then you follow that guard, right. So, side effects are always nasty business, especially if you have to prove the correctness of your program. And the amazing thing is, for a long time when Dijkstra actually coined these, produced these things, for a long time these were used for constructing perfectly correct toy programs. But now this is actually being used in the Ada language. Okay. So, let us summarize the properties of non-determinacy in general and if in particular maybe. So, it is a generalization of the case. You can use arbitrary Boolean expressions as guards. More than one guard could be true at a time. It aborts if if no guard is true. This is for the if. And what it allows you is that a specification mechanism, right. So, it is an excellent specification mechanism, because you do not really, very often the programmer does not want to be bothered about the nitty gritty details of how exactly a computation should be performed and what most of the languages do is that they force you to specify a certain sequence in which computations have to be performed. Whereas often there is, in many cases, there is absolutely no reason why the computation should be performed in that order. Yeah. So you can look upon the if v as a symmetric generalization of the if then else. The if then else itself is a deterministic construct, and it is also a generalization of the case because it allows arbitrary Boolean expressions. And what it does is it frees the programmer from imposing an unnecessary sequencing of operations, but it also makes life more difficult in the sense that it opens a variety of possibilities. So, unless your program is proved correct, by proved I mean proved in a mathematical sense of a proof, unless it is proved correct, there usually is no guarantee that your program will actually work as you intend it to, right. And for example, it is not it will nowhere be specified to the programmer in what order the Boolean expressions have to be evaluated. Okay. One possibility is that one possible implementation is that I take all the Boolean expression, I evaluate all the Boolean expression values, and out of the ones I create a set of indices of the true Booleans, then I run a random number generator program and pick out one. Okay, that is one possibility. Another very simplified possibility is that I just go through the Boolean expressions in sequence till one is true. But there can be any kind of complicated scheduling mechanisms, and the whole idea is that it is a specification mechanism in the sense that since the programmer is not forced to impose an artificial ordering, it means also that the actual implementation is to be hidden from the programmer. How exactly is this if statement going to be implemented is not something that is going to be known to the programmer. And if you want the programs written in this language to be portable, what it means is that it should work under all possible what might be called scheduling policies. How you schedule the evaluation of the Booleans in a guard, in an if or a do statement. So, if you want your so which means if it is going to work under all possible scheduling assumptions and it does not use any other kind of mechanism. So, that is why it is a symmetric construct, both the constructs are symmetric. Means that if you change the order, the program should not change. If instead of writing them in the order B1 arrow C1 to BM arrow CM, if I reverse the order or shuffle the order in any way, the meaning of the program does not change. And if the program is proved correct, then it should not matter either in what order these guards are written or in what order they are taken by the runtime system to execute, right. So, it is a specification mechanism which frees you from imposing an artificial constraint, but then it also imposes it also brings in its own unpredictability of the result. So, if a program is wrong, I mean different implementations could give you different wrong results. I mean, and amazing as it might seem, one of them might actually give the right result because the implementation took a certain decision which happened to match with the programmer's intention of or his presumption of how the guards are going to be evaluated. Okay. So, which all goes to show that it does not mean a damn thing if you actually get the right results from an execution. Yeah. So, so it is necessary therefore the obligation for proof then becomes absolutely essential in such a situation. The moment you have non-determinacy, what it means is that you have to have a proof, and how can that proof be? If the proof is going to be of the form which tries out each and every possibility, then it is not much of a proof, it is just a hand execution. So, what should the proof be like? The proof is something that should exploit the invariant properties regardless of what choice you take. You should be able to specify one single general invariant property of the loop, and regardless of what choice is taken, it should be possible to show that your eventual goal is going to be obtained through that invariant property. Only then the proof has some meaning. So, this construct was actually was created by Dijkstra to be able to develop programs in such a way that program and proof are developed side by side, and the proof leads the way to the development of the program, right. I mean, so the whole philosophy is that it is not that you should write a program and then prove it correct, that is an afterthought, and a proof after the fact is really of no importance except of an academic importance maybe. But what is essential is to use the proof as a guiding tool to develop the program. So, you have to specify invariant properties, you have to do your case analysis at each time, they should be annotating your programs, and then based on that your program should be developed, which is something that we try to teach in the early programming courses. It does not sink in though. So, the whole point is that you have to exploit the property of invariant properties, so that the number of options that you have, regardless of the number of options you have, you are guaranteed that a certain theorem can be proved or a certain goal can be proved, right. So, all this was actually motivated by Dijkstra's own experience in the design of multi-processor, multi-user operating systems, right. So, now if you look upon bringing down various operating system concepts and encoding them in programming languages, which is a very useful thing to do, in the sense that then you can write the entire operating system in that programming language. I mean, you can bootstrap an operating system on top of another. For example, over an ordinary general purpose operating system, you could write a real time operating system. You could, if you wrote a general purpose operating system using non-determinacy, then the portability of your programs also increases. I mean, somebody might just decide to attach one more processor to the current machine, and your operating system should be able to take care of this extra thing. It should not be necessary, for example, to rewrite the entire operating system. So, you should be able to write the entire operating system also in a high level programming language and not depend upon assembly language all the time, which is what is being done right now, right. But the Ada programming language, for example, designed to bomb in nuclear installations in Iraq, right. So, the whole point is that what motivated the design of Ada is that the US Department of Defense found that it has 400, 500, maybe 1,000 installations, and at least 100 different programming languages being used in those installations. It is not a joke, and what they decided was that, so as a result what it meant was that in defense, of course, you keep getting transferred here and there. So, what it meant was that when programmers were transferred from one installation to another, even though the system architecture and everything was identical, just because the programming language was different, they had to spend a few months learning the new programming language, learning how to use the system, and a lot of essential time was wasted. This is a fact, it is a documented fact by the US Department of Defense. And secondly, what it meant also was that you could not move port programs across installations, in the sense that I am having a new Pershing missile installation somewhere, and I can't move the old programs because, well, that system was by a different company and it supports different compilers, and it does not support any of the compilers for which I have installations, right. So, what it meant was rewriting the entire software in a different language, and when you transfer personnel to and fro, what it means is that they spend the first 6 months just coming to grips with a new installation, a new piece of hardware, a new piece of software, a new language, a new system call conventions, new procedure call conventions, and a whole lot of things. I mean, it is a whole society in itself in each installation, and there is very little interaction between different installations. So, what they decided was that, except for their business data processing, I mean, not that they do business, I mean, which a lot of people have accused them of doing, but in the terms of their accounting and payroll and so on and so forth, they found that COBOL was sufficient. But for all their scientific, I mean, they do a lot of research in pure science, right, otherwise you can't do some of the things they do, right, and for all their control systems and for all their non-business applications, scientific, numerical, control, concurrent, distributed, you have a wide variety of installations which have to communicate in a you have to have things working in a distributed fashion. Parallel, maybe you require fast computations which with parallel computers, vector processors and so on and so forth. Reactive, you have control systems which have to react to external stimuli in the form of sensors for nuclear reactors, pressure controllers, temperature controllers, transducers. You have and you have to respond maybe to a cosmic ray shower, and so you require a wide variety of different kinds of applications, and what you have is an explosive variety of programming languages in which all those things are written. And so, for everything other than their business data processing, what they wanted was a single unified language. They went further to say that it should be a Pascal like language which supports concurrency, modules, reactiveness, responsiveness, and therefore, if you are talking of reactive or responsive software embedded in some hardware like a controller for a nuclear installation or a chemical reactor, then what it means is that what that controller gets as signals from various transducers is totally non-deterministic. It is not predictable in a highly decentralized mixture of mechanical, electrical, electronic hardware and software to actually predict when some signal might come from somewhere. And therefore, it is necessary for these controllers or even client servers in a more business like environment, even client servers, I mean take your railway reservation system and so on and so forth. It is not really, when you look at the design of the server or a controller in isolation, all you know is that you might get signals from this wide variety of systems. What you do not know is in what order are you going to get those signals. After all, your controller, the basic purpose of the controller is that if the pressure goes beyond some limit, you have to activate some mechanisms, relays, some electronic switches in order to bring the pressure down. Maybe you have to keep pressure, temperature, volumes and so on in some flow rates and so on in some balance. within certain tolerances. So, when one variable increases, you do not, so you do not really know. So, the controller at the design of the controller, all you will know is what kinds of signals are you going to get, but you do not know in what order are they going to come. And what it means is that sitting as a controller monitoring an entire distributed installation, what it means is that I am subjected to non-deterministic pressures from a variety of places, right. And so, what it means is that I have to have a facility to deal with this, and it is not going to be done by a human being. I mean, imagine in a nuclear installation a human being sitting there and trying to coordinate the entire thing. No, it is all going to be done by a controller written in a mixture of hardware and software. I mean, you go into hardware, there is really no difference between hardware and software, except that when you want some faster executions, time sensitive, responsive. When you have to, the controller will have to activate various procedures within a given time frame, otherwise, I mean, otherwise the whole chemical reactor might burst, right. So, they have to be time sensitive, they have to react to stimuli which come in a non-deterministic fashion in non-deterministic order, and therefore, you require a convenient construct which is symmetric. And since you cannot predict in what order you are going to get these signals, what it means is that your guards, in addition to being Boolean conditions, they would also include, let us say, signal values. Okay. If a certain signal comes, then this response has to be sent somewhere, not necessarily back to the same place, right. You have to activate something else. So, the fact is that any isolated program in a system, in a large system, the only way to cope with the entire system is not to know the nitty gritties of each and every system. After all, that system can keep changing. I might replace something by a faster machine, might replace some mechanical relays by some electrical relays, I might replace something with more capabilities. So, then it is the only way to cope with the entire system is not to know the nitty gritties of each component of the system, but to know only broadly what kinds of stimuli are you going to get, and therefore, what should be your suitable response to it. It is an abstraction that you have to perform, right. So, in a real time, oh, that is another word I should have written, real time. These are all buzzwords, many of them are closely related, overlap and so on and so forth, but they are all different words, right. So, in a real time concurrent distributed environment, which is you have to be in a reactive system, you have to be responsive and you have to do it in real time, right. So, for that you require such a construct. So, the only difference is that the construct also includes communications from outside, and also it includes a timing mechanism, which ensures that if something does not happen within a certain amount of time, then something else has to be done about it. Thanks.